Okay, so section 2.1 is about limits, and 2.1 has 2 days. Most of our lessons have 2 days. Okay, so let's just get right into it. So first thing we need to talk about is average and instantaneous speed. Okay. All right. I have to say something about average speed. It is not what you might think. If you took the SAT, you might remember some questions about how if you're doing, let's say a person's driving to work and it takes them 1 hour, and then they're driving back from work and it takes them 1 hour and 20 minutes, maybe it's rush hour. And then it asks you, or maybe it says something like, okay, they went 50 miles an hour getting there, or 40 miles an hour coming back, or something like that. And you're supposed to find the average speed for that journey or whatever. So they're probably going to give you like a couple speeds or something. You're not supposed to average the speeds. Okay? So average speed has a very specific definition. All right? And it is total distance over total time. All right? This is really important that you not think of average speed as the average of the given speeds. Okay? It's not the same thing. Average speed has a specific meaning, and it's what I said, it's total distance traveled over total time elapsed. Okay, so total distance over total time. Okay, so let's go to that example I was talking about a second ago. Let's say that a person goes to work. So let's just do an example. A person goes to work at 50 miles per hour and returns home at 40 miles per hour. What is the person's average speed? Okay, so it sounds like we are supposed to add 40 and 50 and divide by 2. Doesn't it just sound that way? Average speed. We got 2 speeds, let's average them, right? Okay, so this is what you do not do. So do not go, oh, okay, average speed is 50 plus 40 over 2, 45 miles per hour. Okay, that is not correct. And it's because average speed has a very specific meaning. It doesn't mean this, it means total distance over total time. Okay, so how would you actually do this problem? Well, first thing I want to say is the answer actually does come out pretty close to 45. Okay, but it isn't 45. So it's going to actually be less than that. Here's what you're supposed to do. So average speed would be distance traveling to get there, so we can call that distance there, plus distance back again, okay, divided by time to get there plus time to come back again. Okay? So there and back again by Bilbo Baggins. All right? You saw Lord of the Rings. You catch that reference. Okay, so what we don't know, though, is the distances, right? We don't know how far they traveled there. We don't know how far they traveled back. We don't even know the times elapsed for driving there or back. So it seems like we know nothing. But here's where we can start to simplify things. The distance there and the distance back again are the same because it's to work and from work. So we can just call both of those d. Okay, and then the time to get there is the distance over the rate. So it's distance over rate there, plus, and then the time to get back is the distance over rate coming back. So what we get is basically 2d on top, and on the bottom, d over rate going there, plus d over rate coming back. okay? And the d just cancels out completely. So here's what we end up with. We end up with a 2 on the top, and this is 1 over rate there plus 1 over rate back, which is 2 over, and then we have 1/50th plus 1/40th. Okay, so then you would need your calculator maybe to solve the problem. And it does not come out to 45. So let's go ahead and run this. Let's see, we have 1/50th and 1/40th added, right? And this is supposed to be divided into a 2. The answer is 44.4 repeating miles per hour. So like I told you, it's coming out to around 45, but it's less than that actually. This is not going to show up on the AP exam. Okay, it really won't. But it could be like a number 20 on the SAT. Like the last problem is one of the hardest ones, you know. And it's because 95% of the nation is going to average 40 and 50. Okay? Has anyone ever done a problem like this before? Maybe you have a different method, but you were supposed to find an average velocity or something in honors physics, and it wasn't quite what you thought. Okay. Okay, so this is just kind of a what not to do scenario. But it reminds us that certain words sound like they might mean something, but they actually have a definition. Right? Like average velocity doesn't mean average of velocities. It means distance over time. Okay, so just a word to the wise. Okay, can I move forward on this problem? Okay, so let's go on and talk about average and instantaneous speed. So we just basically said that average speed is total distance over total time. Over total time. And the symbols for that in math would basically be delta y over delta t if delta y represents change in position. Or actually, total distance traveled isn't necessarily delta y, but delta y would be like what we call displacement. Do you guys remember that word? Displacement. Okay. But in an object moving forward, okay, with like a positive velocity, you can just think of it as delta y over delta t. All right. So it's like the change in the y value divided by the change in the time. So let's take a look at an example real quick. So let's say that you were told the equation, and I abbreviate equation EQN. The equation of motion for an object dropped from a height of 200 feet is y equals 200 minus 16t squared. So you might recognize that 16, that's 1/2 g if you're in physics honors. Remember, it's initial position plus v naught t minus 1/2 at squared. Doesn't really matter. They gave us the equation, so you don't need to know any physics right now. Okay, so this is our function for finding like how far the object has dropped. Okay, what is the average speed of the object during the first 1 second? Okay, so what is the average speed of the object during the first second? And then we can say, how about the first 2 seconds? Okay, so what you might want to do on this is just kind of form a table for the first 2 seconds. So we know that if t is 0, right, we're going to get, for y, 200 minus 16 times 0 squared. Not very interesting. This just comes out to 200. This just means the height of the object is 200 before you drop it. You started at 200 and you hadn't dropped it yet. So the height is still 200. The first second has elapsed, and the object's been falling for a second. We get 184. And after 2 seconds of fall, the height of the object is 136. Okay, so these are just feet. Units are actually a really important part of this class. Super important that you pay heed to your units. Okay, so we'll talk about that plenty. But okay, so what is our velocity or average speed, during the first second? Okay, so when you hear first, the implication is that you're talking about at the first second, and you're comparing that to the time 0, right? So if I say the first 2 days of school, we're talking about day 1 and 2, which come right after day 0. Okay, so you're technically dealing with delta t as first second minus 0th second. So during the first second means between time 0 and 1. Okay, so delta t would be that. Delta y would be 184 minus 200, which is negative 16. Okay, so how did I get that? I just subtracted the two y values, y1 and y0, I guess you can say. Okay, and then you would form a fraction. So your average velocity, we'll just use v for velocity, even though they're not asking for dimensions, like direction, Okay, so this comes out to negative 16 feet per second. Okay, so what does this number mean? Well, it's just saying that, look, you dropped it, right? And it was originally not even moving. And then all of a sudden, gravity's grabbing onto it, right? And it's moving, moving, moving. It's speeding up, speeding up, speeding up. And then at the first second, you ask, all right, during that whole first second, what was the speed? Well, there was many speeds. There was the speed 0, and there was the speed 1 foot per second, and there was, a speed, 5 meters per second, or whatever, 2 feet per second. All sorts of speeds. But on average, what was the speed? For that, we look at the endpoints. We say, okay, well, at the first second, it was at 184 feet. At the 0th second, it's at 200. It moved 16 feet. 1 second has elapsed. Can someone tell me what the negative means here? Yeah. Down, right. So the negative always means something in math, right? It usually has to do with the direction. Okay, yeah, so it just means negative 16 feet per second means 16 feet per second in the downward direction. So we really did get a velocity there. Okay, let's talk about the first 2 seconds. Okay, so first 2 seconds. So for that one, you're comparing times 2 and 0, right? Okay, so you're going to be taking not 184 minus 200, but 136 minus 200. And the second minus the 0th second. That's what first 2 seconds means. And this comes out to negative 32 feet per second. Okay. So this is not very difficult. It's a definition, okay? So when you're done with your notes, right, you're doing your homework tonight, the first problem is this problem. Except it's a different equation, different amount of time, perhaps. But listen, you got an equation already, okay? This is our first formula, right? Total distance over total time is average speed. Okay. Let's go on and talk about instantaneous speed. So what was the instantaneous speed at the instant 3 seconds? Okay, so listen, this is asking not what has happened on average during the first 3 seconds, but the ball has been falling, right? And we want to know the exact speed of the object at the 3rd second. Okay, so this puzzled people for a very long time. Okay, so let's just talk about this stapler for a minute. If I were to drop this stapler, right, I could talk about how far it moved in the 1st second. I could talk about how long that took, right, 1 second. I could then figure out average velocity using my new formula, right? I could do that for the first 2 seconds. I could even do this between seconds 1 and 2, right? I could find delta y and delta t just for the between the 2nd and 3rd second, or the 15th second and the 18th second. So I have this neat formula, but what is the speed of the object at a given instant? That's a totally different question, okay? Let's just try it with what we know so far. We're going to run into some problems. Let's see what happens. Okay, so velocity average. Let's see, total distance traveled. Let's see. Okay, well, the object at the 3rd second is at what we would call y of 3, right? And then we're comparing that to the 3rd second, I guess. Y of 3. And the time elapsed, well, let's see, the difference in time is the 3rd second minus the 3rd second. No time has elapsed between the 3rd second and the 3rd second. An instant is exactly that. It is 1 instance in time. So we have a very interesting scenario. We get 0 over 0. And 0 over 0 is equal to what? Is it 1 or 0? Or is it undefined? It's undefined. Okay? So you have to be really careful with 0 over 0. We're going to run into 0 over 0 all year long. And 0 over 0 is not 1. It is undefined. Anything over 0 is undefined. So that didn't work at all, right? Okay, so Newton is responsible for figuring out how to do this. Okay, and so this is sort of calculus right here. So what we're going to do is scratch this whole solution. This doesn't make any sense. Newton is basically saying this: the velocity at an instant is going to be the limit as h goes to 0. Now, he didn't necessarily say it exactly like this, but his thought was this: y at 3 plus h minus y at 3 over 3 plus h minus 3. Okay, so what does this mean? This means we're going to evaluate where the object was at 2 times. You might say, well, hold on, we can't do that. We're looking for the instant when t is 3. Why are you looking at 2 different times? Well, you can think of h as a hair, 1 hair on a human head. Okay? This is like at time 3 and time 3 plus a hair. Okay, just a little bit after 3. Just a tiny, tiny, tiny bit. Okay? All right, so how would you evaluate this? Well, you'd plug it into the function, right? Okay, so you would start by doing 200 minus 16 times, and you would put in 3 plus h, and then for y of 3, it's 200 minus 16 times, and then we plug in 3. And what's neat about this is, even though we know that the time elapsed is very, very small, we don't actually need to consider how small. Because what we're going to find out in a minute is this all cleans up real nice. Real nice. It's going to clean up real clean for us. And then we're going to make h 0. Okay, so Newton was very clever. All right, so let's go ahead and work this out. So this is algebraic stuff, okay? This is where your algebra has to be strong, right? So this is 200 minus 16 times, and this needs to be FOILed. So it's 9 plus 6h plus h squared. Minus, and the other one is just 200 minus 144, because 16 times 9 is 144. The bottom is just actually h. The 3's cancel out down there. Okay, so let's work this out. So we have 200 minus, I got to distribute this 16 here. So 200 minus 144 minus 96h minus 16h squared minus 56 all over h. Okay, my goal was to kind of clean this up. Well, if you look closely at it, it's starting to clean up already. The 200 minus 56 is 144, and then there's a minus 144, so all of that cleaned up. And we can factor out an h on the top. We could factor out a 16h if we like. I'm only factoring out an h. Okay, so this is like magic. The h actually cancels out of the problem and leaves us with negative 96 minus 16h. See? Now, what this means is the average speed between the third second and 3 plus a hair is that. This is the average speed. I would like to talk about the third second. I don't really want that extra hair of a second. So now I'm going to make h 0, and I've got my answer. Okay? So let's make, we're going to now do the limit as h goes to 0, negative 96 minus 16h. And basically this is just like saying what would happen if h were to shrink and become 0, and we just get negative 96 feet per second. So if you took Ms. Fusco's class, right, you were given a fab 4, okay? You were given final velocity squared equals initial velocity squared, either plus 2AD or minus 2AD, depending on how she taught it. You had final velocity equals initial velocity plus AT. You had initial or final position equals original position plus V naught T plus 1/2 AT squared. And then there's a fourth one too that doesn't get used quite as much. But those formulas come from this, okay? So I just want to tell you that you don't need those formulas ever again. All of them come from this. You might need them for a couple more months, the Fab 4. But they come from doing something like this. And so Newton didn't know anything about those formulas, okay? He knew how to do this. And then from his work, where many equations were developed from there, see? So calculus is a really interesting thing. The whole limit idea allows us to create formulas. You'll find that out later. But that's kind of neat. We were talking about the third second and something slightly after that, but in the end, we ended up talking about the third second. And so that was a huge contribution by Newton there. And there are centuries of history between the first question we asked today and this one. There's years and years passed by before they figured out how to do this. Okay? All right. Any questions on that process? That'll get you through like the first couple homework problems. Okay, yes?
What does the H stand for? Is that just
It doesn't mean hair, but you can think of it that way. Okay, so I use a lot of things like that. I'll say how you can think of it. But it's like the H just stands for a slight time delay after the third second. Because we can't talk about the third second compared to the third second. Remember what happened when we tried that, remember? Yeah, we had trouble with that. We got undefined from doing that. We cannot talk about this. It doesn't make any sense. So we kind of cheated it. We kind of cheated the system. We said, okay, well, we won't talk about 3 and 3. We'll talk about 3 and this little time after that called 3 plus h. We'll find the average velocity, and then we'll make h 0, which brings us back to talking about 3 and 3. Beautiful. It's very clever. It's a workaround. It's a workaround. It's a cheat. Okay, very interesting. So that's kind of our first example, and it's a long one. But it is centuries in the making, actually. That was quite an accomplishment. All right, let's go to this LIM symbol. What is that thing? So how many of you have seen that LIM symbol there? Okay, how many have not seen that before? LIM. Okay, so the LIM is pronounced limit, right? So let's talk about the definition of limit real quick. Okay, so the basic idea, if you just want an intuitive understanding of what a limit is, it's basically the y value that a function approaches when x approaches a certain value. Okay? The verb we use is find. So find the limit. Okay, sometimes we say take the limit. I don't know why. We do the same thing with the word derivative. Sometimes we say find the derivative, and sometimes we say take the derivative, and sometimes we say differentiate. Well, we never say limitate. But if we want to find a limit, we say find. Or take. Sometimes we say take. So I want to just say that kind of stuff because sometimes you'll hear a teacher say, okay, take the derivative. And everybody's like, take the derivative where? Where am I supposed to take it? It just means find the derivative. All right. All right, so let's try a problem like this one. It just basically says find the limit of f of x equals x cubed minus 8 all over x minus 2 as x approaches 2. Okay, so the way we find a limit is not what we did a minute ago. I needed to teach average speed really early, but we're deviating from that idea. Right now, we're not talking about that at all. So you cannot use your first formula for this, okay, or even that limit thing we did. We're just trying to figure out the limit. So what does this mean? It's saying this, look, this function, right, if you give me an x, I can tell you what y is, right? If you give me x, I can tell you what y is. Okay? Except if you give me 2. If you give me x equals 2, I won't be able to do much with that. Why is that? It's going to come out undefined. It'll actually be 0 over 0. But as long as it's anything over 0, I can't really talk about x equals 2. It's not in domain. But I can talk about any other x. But it's possible that the graph, even though there's no point at x equals 2, it might look like it has a point at 2. Let me show you what I mean. So if you were to pull out your graphing calculator right now and enter this thing, this is my calculator right here. You don't have to write this down necessarily, but I just want to show you why this question is even being asked. Okay, we're talking about x equals 2, okay? And if you look over here at x equals 2, let me enlarge this. It is an interesting question. So even though the answer is, if you're asking like what is f of 2, the answer is definitely doesn't exist. But if you look at x equals 2 on this graph, right, it certainly looks like there's a point there. In fact, I might even say it's at 2, 8. It seems like it's going to be 8. Okay? You guys see that? I mean, it certainly looks like there's a point there. But if you check a table of values, you'll find there is nothing actually there. Here's the table of values. If you go down to x equals 2, there it is, undefined. It says right there, undefined. Okay, so graphing calculators and graphing softwares often can't do this, but it should have probably put a little open hole right there where my mouse is. There should probably be a little open bubble there, because that point doesn't actually exist. But it certainly looks like there's a point there. Okay, so let's go back to the question at hand. So the answer is probably going to come out to 8. All right? So here's what we're talking about. If you were to take that table that I had a minute ago and copy it from your calculator screen, so you have x and you have y1, right? I assume you guys know how to type these in. So Just don't forget your parentheses when you type this stuff, right? Okay. If you were to look anywhere near 2, you would see that this comes out to 10.84. And at 1.9, we have 11.84. And at 2.0, unfortunately, we have undefined. Okay, and at 2.1, we have 12.61. You can just copy this stuff down. And for 2.2, it's 13.24. If you look at what's going on, what's sort of trending on the left and the right, you can figure out what the limit is. Okay, so when you are near 2, so let's say 1.9 and 2.1, the y value is near 12, right? You can see that. So okay, 1.9 is like 11.8, 4. And then when you get to 2.1, which is just on the other side of 2.0, it's 12.61. So if you had to guess what was sandwiched between 11.84 and 12.61, you might guess it's like 12 or something, right? This is not a great way to find the limit, but it sure seems like 12 would be the value that goes here if it weren't undefined. You guys see what I mean? It seems like it's right somewhere in there, 12. So how do we show that it's exactly 12? Okay, so my guess is I'm going to put, is the limit 12? That's my guess. Okay. Well, from this table, I can't really tell exactly. I mean, it could be 12.1, right? And I can't just average 11.84 and 12.61. This is not a linear function. So what am I going to do? Well, what I need to do is find a workaround. It turns out that this expression actually simplifies. You might not have caught it at first, but it does simplify. So let's take a look at how that might work. Okay, so a lot of times what you need to do is factor these. Okay, so how do you factor a difference of cubes? So this is just a skill that you learn in Algebra 2. So if you have a cubed minus b cubed, how do you factor that? Well, a squared minus b squared is easy, right? It's a plus b and minus b. A cubed minus b cubed is a little different. We use that SOAP rule. If you guys remember SOAP, how many of you have heard of SOAP? Okay, you don't really need to know SOAP. You need to know how to factor. So I'll show you what it means. But it means same, opposite, always positive. Same, opposite, always positive. So we're definitely going to have an a minus b. A minus b. In order to get 3 powers of a, I definitely need another a squared. So that's definitely needing to happen there. And I'm going to need a b squared eventually to get my b cubed. And what goes here is ab. 2ab. No, just ab. Yeah. Just ab. Okay, so this is a really obscure factoring pattern, and a lot of people don't remember it. But what we're saying is that this factors into x minus 2 and x squared plus 2x plus 4. Okay, now you might freak out and say, I'm not going to be able to reproduce that. You can also use synthetic division. Okay, so this is a pre-calc skill that sort of circumvents the need for this. But let's say you couldn't remember how to do this factoring. I'll do the same thing in purple here. So let's say you wanted to factor x cubed minus 8. Well, you can guess that one of the roots to this is 2, right? Obviously 2 makes this come out to 0. So you can assume that x minus 2 factors out. And you might say, okay, this is the part I can't figure out, like what goes next. Well, why not just use synthetic division? So x cubed minus 8 represents 1x cubed, no x squareds, no x's, and a constant negative 8. Okay, so you can just bring this down. Remember doing synthetic division, right? 1 times 2 is 2, and then we add. 2 times 2 is 4, and then we add. 2 times 8 is 8, and then we add. And the remainder is 0, as it should be. And this represents 1x squared plus 2x plus 4. So here is your missing factor if you just can't remember SOAP. I don't really have time to teach SOAP again, so if you need help with SOAP, come ask, or try synthetic division like I did here. You do have to guess one root, but that's easy. Oh, what cubed minus 8 is 0? It's like, okay, 2, right? Usually you can guess that root pretty easily. Okay, so back to the drawing board. Why did I do that? Well, now, see, this cancels out. So this problem actually just comes out to this, x squared plus 2x plus 4. Okay, so what does that graph look like? I'm kind of curious what that graph looks like. So I'm going to go to my graphing calculator, which is right here, and I'm going to add another function, and it's going to be x squared plus 2x plus 4. Let's see what that looks like here. Where is it? Wait a minute. Okay, that's the first graph. Let's turn on the second graph here. Wait, it's the same graph. Hold on. Let me turn off the first graph. Okay, there's the second graph all on its own. Okay, now let's turn this one off. Let's turn on just the first graph all on its own. It's the same graph. Yeah. You just reduced the fraction. It doesn't change the graph. The only thing that it changed is now when you do this parabola x squared plus 2x plus 4, that point is filled in. Okay? So that point is actually there at x equals 2 now. And now we can just find f of 2. Okay, so what I did is I kind of cheated. I rewrote this problem into a problem that I can plug 2 into. See? now I can plug 2 in. See what's going on? Okay, let's do it. So it's going to be 2 squared plus 2 times 2 plus 4. Sure enough, it's 12, just as we had predicted. Okay, so I'm not using a lot of calculus symbols right now. I'm showing you that certain things can factor, and maybe you couldn't plug in 2, but now you can. You factored it, it reduced, plug in your 2. Okay? All right. Here's how you should write this mathematically. You should have written this, LIM as x goes to 2 of x cubed minus 8 over x minus 2 equals, and then you write LIM as x goes to 2 x minus 2 times x squared plus 2x plus 4 all over x minus 2, and then you would cross these out, and then you would write equals LIM x goes to 2 x squared plus 2x plus 4, and then you would plug in the 2. 2 squared plus 2 times 2 plus 4. You don't need any graphs. You don't need any tables. You need to factor it, reduce it, and plug in the limit value. Okay? The only reason I showed the table was to convince you it might be 12, and it helps kind of understand what this means. And the only reason I showed the graph was, again, just kind of show you that I believed it was 12 in the first place, and sure enough it is. Okay? So it's not 12.1, it's actually 12. Okay, so this is what the graph looks like in the end when it's all said and done. You've got a graph. Okay. At 2, let's just make this 12, 10, 14. Okay, at x equals 2, there is no point, but the graph appears to pass through this point. Okay, that's what's going on. It appears to pass through this point. So if I asked you what is f of 2, you would say there's no such thing. But if I say what is the limit as x approaches 2, you would say 12. So what is a limit? Limit's just basically saying what does it appear that the graph is at x equals 2. If that hole would fill, you know. Okay, so that's what that means. Let's just try another example of that. How about sine x over x? This is a really famous one. So I'm just going to switch to the calculus notation now. And what if I asked you, instead of find the limit, okay, I will write LIM, okay, LIM, x goes to 0, sine x over x. And it basically is a faster way for me to write the question. It means, what is the y value of this function when x is near 0? Well, if you want to try plugging it in, you can. In fact, it's not a bad idea. Let's give it a try. So this is try number 1. Let's just plug in 0 here and see what happens. Oh, that didn't work out so well. It gives you 0 over 0, which we said was what? Undefined. Okay, so you might say, why'd you do that, Mr. Shore? Because that's actually the first thing you're supposed to do. You're supposed to just see if you can plug it in. If you plug it in and you get an answer, you're done. No need to factor, no need to graph, no need to look at the tables, no need to think. Just plug in the number. So that's actually the first thing I always try. Or at least do it mentally. Okay, try number 2. Try and factor it. Okay, let's see here. Sine x over x. All right, let's see. Let's factor sine x. Okay, not too sure what to do there. There is a way we'll learn to do this much, much later. Sine x can be written as an infinitely long polynomial, and the x cancels out. But we're not nearly ready for that. That'll be like March. We'll write the Taylor polynomial, and we'll cancel out that x. And then we will plug in 0. So try number 2 kind of failed. Shoot. How many of you have heard of L'Hopital's rule? L'Hopital's rule. Okay. If you know how to do derivatives, you can actually cheat and finish this problem in about 2 seconds. But we don't know how to do derivatives yet, supposedly. Okay? So we're just going to have to take it the way the ancients did and talk about the y values near x equals 0. So let's just look at the table. Doesn't look like we have much choice. Okay, so if you plug in negative 0.2, it gives you 0.9935. And if you plug in negative 0.1, you get 0.99833. If you plug in 0, doesn't work. If you plug in 0.1, you get 0.99833. And if you plug in 0.2, you get 0.99335. Okay, so let's just kind of look at the trending here. When x is near 0, y is near what? Look at the y values, 0.9935, 0.99833. What do you notice? Very close to 1, right? Okay, so you could ask, is the limit 1? And for this one, unfortunately, right now, I have to just say, yes it is, believe me. I can't show you this proof for it right now because it requires at least one skill we don't have yet. But this is such an important limit that we have to just memorize it for now. Okay? So the answer to this question is yes, no proof today. Okay, stay tuned for the proof much, much later. If you really want to be convinced, you can actually look at the graph. The graph looks something like this. And right here near 1, the graph basically is looking like this. And I mean, when you're near x equals 0, it is so close to 1. It's very convincing visually. But that's still not proof. But we're just going to say yes. And this one we are going to memorize for now. Okay? The limit as x goes to 0 of sine x over x is simply 1. We don't get it by plugging in 0. That actually gives us undefined. We get it from looking at the table, and there are many proofs for this. We're not ready for it yet. Okay, so we're going to memorize that one. We're going to memorize average speed, right? And what was the other one? Oh, the factoring trick. Okay, and this will get you through your first assignment. Your first assignment is, incidentally, right here. So I'll just put it up. It's also on Edmodo. And it's page 66 and 68, you got 1 through 4. Those are just asking about speed, which is what I did at the beginning. And then 45 to 48, 71 through 74 are limit questions, I believe. Try not to use your table feature on 71, 72, 73, 74. And on 76, try not to use your graphing feature. Try to use your table feature. I assume you guys know how to graph on your calculator? Do you guys know how to make a table? Okay. I have a second, but this is something I can help you with if you need. Making a table is just something you do instead of pressing graph. You can press table, but you have to know how to set it. You have to go to table set. I should have used it quite a bit pre-calc, but looks like my emulator's crashing. Let's try it again. Well, I'll just write a note to you here. So you want to go to table setup. It's called TBL set. And you want your table start, TBL start, to be that limit value. So for my first problem, that was 2. And then for the second problem I did, that was 0. Okay. And then for your delta TBL, delta TBL, you want to set that to be something small like 0.1. That's what I was using, was 0.1. And then under y1, you enter your function. You know, sine x over x, and then you press table instead of graph. And you'll see this. So why don't we just set it equal to 0? This would be for that last problem. You can get the same table I got by going to table setup, doing table start 0, delta table 0.1, and then just go back to y equals and punch in your function, press table. Okay. I can help with that kind of stuff, technology stuff, if you need.